So here we go. The first one going from 2.3, I mislabeled that. That should have been gallons. So just G. We'll come back to that one. The second one, 4.8 meters to feet. So 4.8 meters, put it over 1. In our conversion factor, we want meters on bottom and feet on top, but we also prefer to have the conversion factor that has 1 meter in it. The denominator is 1. So what conversion factor gives that? 1 meter equals what? 1.0. We don't have anything to feet? 3.28 feet. That'll work. Goes directly into feet. The 1.09 yards would get us to yards, and we'd still have to convert to feet. This will give us a little bit less round off.
The meters?
Yep.
Here in the book, go to page 576.
Yep. If you look at it, there's a bunch of them on the other side of the table.
I like the math lab one.
They have a little bit bigger. They have a little bit bigger table in my math lab, don't they? Yeah, on 576 in the book. There it is. If you look on the right side, yeah, the third one down on the metric to US, 1 meter is approximately 3.28 feet. So then, there's nothing, all we have to cross cancel is our units. So the meters cross cancel out. 4.8 times 3.28. That sounds about right. Yeah, 15.744. And of course, my math lab would say round to the nearest tenth or hundredth of a foot, or whatever. So that one is done. 7.3 kilograms into pounds. So we're going to put that over 1. Kilograms on bottom, pounds on top. Again, 1 kilogram is 2.2 pounds. So we get what? 16.06 pounds. Again, kilograms cancel out, and it's just 7.3 times 2.2. Yes? Yeah, my math lab would always tell you to round to the nearest tenth or hundredth. On a test, usually I have the answer key set up so I can round it to whatever. So on a test, if you just go to at least 1 decimal place, you're okay. So for then the 2.3 gallons over 1. So we're going to put gallons on bottom here to liters. 1 gallon is 3.79 is what this book uses. So the gallons cross cancel. It's 2.3 times 3.79, which is 8.717 liters. Very good. Any questions on making conversions? Okay. We did talk a little bit last week about some of our units, other than the standard units, dealing with some basic compound units and temperatures and stuff like that. Sorry, my pen slipped away on me there. Converting temperatures Fahrenheit to Celsius and back and forth, we couldn't use just a simple conversion factor like we're using here. We had to use formulas. For example, if it is a 72 degree Fahrenheit day, what is that in degrees Celsius? Well, degrees Celsius is degrees Fahrenheit minus 32 and then times 5/9. So we're going to put 72 in for degrees Fahrenheit. 72 minus 32, which will give us 40. So then 40 times 5/9 is? What's that?
How do you want to the fraction?
Well, if we leave it as a fraction, what's that going to be? 4 is going to be 22 22 and, so 22 and 2 ninths degrees Celsius. So 22.22222. 9 divided by 5 is 1.8. So in the book, it probably has f minus 32 divided by 1.8 like that. Or 5 ninths.
70 degrees Celsius to Fahrenheit.
Yep.
Use the formula F, which is 1.8 times C, and then you have 30.
Oh, you're going the other direction though. You're going from Celsius to Fahrenheit.
So for Fahrenheit to Celsius, it says use the formula 5 times F minus 160.
Oh, they're just multiplying. What they're doing is they're taking the 5 times F and the 32. So it's 5F minus 160 and then all divided by 9.
Yeah.
Yeah. They're just making it a little more work for you. Okay. Any questions on doing our conversions and stuff like that?
What was the answer to that one?
To that one? 22.22. Okay. So what we're going to look at today is we're going to actually go from measurement into a little bit of basic geometry. And in geometry, we've talked a little bit about some of this before, but in geometry, our most basic principle is that right there. Not just a dot, but what is called a point. A point has several properties. First of all, it marks a location, and it has 0 dimensions. So all it has is a location, a position. All of geometry, however, is built from that dot. For example, if we take a dot and we pull it in a single direction. Now, a lot of people would call this a line, but it's actually called a line segment. If you labeled the ends A and whatever you labeled the points, A, B, whatever, that'd be line segment AB. If it's CM or whatever, line segment CM. Whatever the labels of the points at each end are is going to be the name of that segment. A true line goes on forever in both directions, by the way. We define the length of that segment. It doesn't make sense to use true lines because everything we do begins and ends somewhere. So the length of that segment is equal to the distance that the point moved. We started at point A and moved to point B. That distance that it was moved is the length of the segment. Now we could take that point, let's call this point P, and go in a single direction and just keep going. That would be called a ray. And we name a ray, like we called this one segment AB. A lot of times we label it AB with just a line above it, a segment above it. A ray has to be named, and of course we could call that segment AB or segment BA, it doesn't matter. Because we really don't know which point we started at and which point we ended at when we moved our point. Could have been we started at point B and moved to point A. But for a ray, we start at one point and we go on forever in a single direction. To know which direction we went in, we have to name a second point. Let's call this S over here. So that's point S. So this is ray PS, like that. And for a ray, it has to go in that order. The first letter here has to be the end point or the starting point of that ray. We know what direction we move to make a ray. Now, if there's another point out here, let's say this is point T out here, I could have called this ray PT. Wouldn't make a difference. PS, PT, as long as I name the end point first and any other point along that ray. Now, a ray looks a lot like what we called a vector back when we were talking about integers, positive and negative numbers. And it is. Now, when we were talking about integers, that vector could have only one of two directions, positive direction or negative direction to the left. In geometry, we start getting plane geometry where we have, not only side to side, but up and down. That ray has two different properties we can talk about. We can talk about its length. We define that as, if it's a vector, it has a length. A ray actually goes on forever. A ray going on forever, the length is kind of a useless point because it has an infinite length. But we can also talk about its direction. And its direction is defined basically off of navigational directioning. The east direction is defined to be 0 degrees. And of course, a complete circle is how many degrees? 360. So this here vector might be at 18 degrees. That's its direction. So let's say I have a ray. I'll use it as a vector. The ray would give it a direction. Let's say I come back to that same starting point. Let's call that point M. We'll put a point out here. We'll call it point N. And so I'm going to come back to that same starting point, point M. And I'm going to move in a different direction this time. I'm going to take that same point and go in a different direction like that. Let's put point P here. So I have two rays. I have ray MN and I have ray MP. Since those two rays have the same starting point, they both start at point M, they form an angle. The angle has, three parts technically. It has the vertex, which is that common starting point, point M. And then it has sides. This would be side MN and this would be side MP. If I want to name the angle, we label it with that little angle symbol like that, then I name one of the sides. So let's go P. Then I have to name the vertex, M and then N. So angle PMN is the name of that angle. I don't have to name side P first. I could have named side N first. NMP would also be a name of that angle. And of course, if there were any other points along either of those sides, I could use those points. As long as I name a point on one side, then I name the vertex, and then I name a point on the other side. So the big concept, I know the naming part's kind of basic. The big concept is how big is this angle? Well, the original way of determining the size of an angle was off of that direction that we discussed right here. Let's say that this, again, is our 0 degree, our east direction. Let's say this angle here is at 28 degrees. That ray is at 28 degrees. Let's say that this ray here is at the direction 79 degrees. Well, then the angle here is the difference between their directions. If this is at 28 degrees and that's at 79 degrees, 79 minus 28 is 51 degrees. So this would be a 51 degree angle, the difference in their directions. Now this is kind of an old-fashioned definition of angles, but that is the original definition of angles, just a difference in directions. It was very useful years ago when most people had some understanding of navigation. They knew that 0 degrees was east, 90 degrees was north, 180 degrees was west, 270 degrees is south. How many of you have used any sort of navigation like that? Okay, maybe one or two of you. So that's exactly why this is an outdated way of defining angles. I show it to you just because it's nice to know where it comes from. And it does make sense if you're familiar with direction, using angles for directioning. Our modern version of defining an angle goes off of what we started earlier, A complete rotation is 360 degrees. So, if I start in one direction and I rotate to where I'm pointing exactly in the opposite direction, that's going to be 180 because it's half of 360, half of a full turn. If I start in a single direction and I rotate so that I've made a square corner, that is 90 degrees. So any fraction of a full turn can be defined as that fraction of 360 degrees. This one right here that makes a square corner has a very special application in geometry. It's called a right angle. It is symboled like this. You put a square in there to show that corner is square. Also, it can be said that those two rays that form it are perpendicular. Perpendicular means that they intersect or they meet at a right angle. Now, perpendicular is actually more powerful than a right angle. Right angles just means in two dimensions they make 90 degrees. Perpendicular would be described as three dimensions. For example, if I have a line coming out of the paper coming straight at me, so it would look like a dot if you were looking at it. Perpendicular would mean it forms a right angle in every direction. If you look at it this way, here's my line coming out of the paper. It would form a right angle here, but also up here and over here. And no matter what direction you measure the angle between that line and the piece of paper, it's going to be a right angle. That's perpendicular. So that right angle, 90 degrees, is an important dividing point for us. If I have something that forms an angle smaller than a right angle, it is called acute. I think of the word cute means usually describes things that are small, so acute angle is smaller than 90 degrees. An angle that is larger than 90 degrees is obtuse. Another application of those words is in describing someone's thoughts and thinking. An acute thinker is someone that focuses in on a very narrow picture and can see all the details. An obtuse thinker is someone that sees not only the big picture, but all the other possibilities off on the sides. That's when they say you're an obtuse thinker. You see the whole picture and some of the subsidiary items. I can't talk tonight, sorry. Time for my nap. Okay. Most people don't realize it, but it is possible to have angles bigger than 360 degrees. If I have this here and I've labeled this as 31 degrees, this angle could be 31 degrees, or it could be 360 plus 31, or 391 degrees. Doesn't matter. It could wrap around 5 or 6 times and come back to there, couldn't it? Wrapped around 5 times, it'd be 1831 degrees. Well, the key is we don't care. We usually talk about something called the smallest or simplest angle. For our purposes, all of those possible angles behave exactly the same as the 31 degrees, so we're just going to use the 31 degrees. Now, we're not going to get into trig or anything like that in here, but in trig, 31 degrees and 391 degrees would give you the same results of any trig function. So there's no reason to distinguish between them. So we're going to use the simplest one. So some things that we can look at, some types of angles we can look at, some relationships we can have. If I have my starting point and I have 2 rays formed from that starting point, of course, gives us an angle. But I could have a third ray from that same starting point. So if this angle here is 41 degrees, and this angle down here is 28 degrees. Now I can find this whole angle here to be how much? 69 degrees. I'm just adding the 41 plus 28. Gives me 69 degrees. Likewise, if I have an angle that is defined to be 79 degrees, and I cut a new angle in here that is 24 degrees. This angle here would have to be what? 55. We take 79 degrees and subtract 24 degrees. Gives us 55 degrees. So let's say this is 31 degrees. This is 39 degrees. What's this angle here? Careful. Can I add 39 and 31 and get 70 there? No, I can't. Yeah, they're not starting at the same point. The reason I can add these angles here to get 69, and the reason I can subtract these angles here to get 55, is because they share a vertex and they share a common side. That is what is called vertical angle, or not vertical, sorry, adjacent angles. Adjacent angles can be added and they can be subtracted, but they have to share a common side and a common vertex. This one here, even though it does share this portion of a side, the vertex is not in the same spot. We can have more than one angle, or more than two angles in a set of adjacent angles. So this could be 32 degrees. $51 degrees. And this here could be 108 degrees. What's this angle here going to be? I'm going to take the 51 and 32. I have to get 83 degrees. So from here to here is 83 degrees. Then I have to take that away from the 108. So 108 minus 83 is 25 degrees. What do you think? Oh, we got a ways to go yet. This is 158 degrees. This is 71 degrees. I will define this one here to be 63 degrees. In your notes, find that angle. So what'd you come up with? What's that? 24. So we've got 63 and 71. That's 134. So 158 minus 134 is 24. So 24 degrees is correct. We can have special relationships of adjacent angles. when two adjacent angles add up to a straight line. I add up to a line. I shouldn't say straight line. That's kind of redundant. All lines are straight. If it's not straight, it's a curve, not a line. So anyway, if this angle here is 39 degrees, and we know, of course, that this is a line, this angle over here has to be 141. Good. We know that that's a total of 180 degrees. We subtract 39 to get 141 degrees. A combination of two angles, whether they're adjacent or not, that adds up to 180 degrees is called supplementary. Now, when you see them visually and they form a straight line, it's easy to remember that they add up to 180 degrees. But we could have an angle is 109 degrees. Find its supplement. Well, the supplement is going to be 180 minus 109 for 71 degrees. Another possibility with our adjacent angles is we could have adjacent angles that add up to a right angle. 90 degrees, you got it. And let's say this angle here is 54 degrees. What's this one got to be? 26. Good. 90 degrees minus 54 degrees is 26 degrees. So this is 26 degrees. Now again, they don't have to be adjacent. Any combination of angles that adds up to 90 degrees is said to be complementary. Now, if you're anything like me, I always struggled. I knew the words supplementary and complementary, and I knew one was 90 degrees and one was 80 degrees. But trying to remember which one was which was a chore for me. The way I remember it is you get complements when you are right. So complementary angles add up to a right angle. So let's say an angle is 17 degrees. Find its complement.
That's 36, by the way.
What's that? This should be 36? Oh, sorry. 36. Thank you. There you go. 36 degrees would be its complement. That does add up to 90 a little bit better, doesn't it?
Mm-hmm.
Sorry about that. So down here, the complement is 17 degrees. 90 minus 17 is 73. Hopefully I got that one right. Okay, thank you. So with this combination, especially with the supplementary angles, we can run into a set like this. If this angle here is 53 degrees, what else can I find out about this set of lines and the angles? Okay, this one here is also 53 degrees. How do we know that? Okay, they're two straight lines. If you think about them, if you have one straight line, I don't know if this will let me rotate or not. Probably not anymore. Here, let's do this. The new version of Word doesn't do the same stuff anymore, so I've got to... Yeah, it won't let me do it. Doesn't have that option anymore. When I draw it, it won't let me rotate them. But anyway... Maybe this will let me rotate. There we go. Nope. Oh well. So anyway, get back here. We'll just do this manually. If I start here, if I take this half of the line and I rotate it to here, this half has to rotate the same amount, doesn't it? So whatever angle is formed here has to have the same angle formed here. That's called vertical angles. They're angles that are formed by the same rotation of two lines. There's another way that we could find that this is 53 degrees. We don't necessarily have to know that information about vertical angles. We know that this is a line, correct? Therefore, this angle and this angle have to add up to 180. So 180 minus 53 makes that 127 degrees. Well, we also know that this is a line, right? So this angle and this angle have to add up to 180. 180 minus 127 is 53 degrees. What do you think this one has to be? That's 127. Again, because it is supplementary with the 53 degrees. 180 minus 53. Well, you notice our vertical angles come in pairs. These two are vertical. They're the same. They're across from each other. But these two are also the same. They're also vertical angles. So whenever two lines intersect, four angles are formed. But they come in pairs. Once I know one of those angles, I know all four. Let's say this one here is 78 degrees. Well, I can find this one very quickly to be 78 degrees. Then these two are just going to be the supplement of 78. This is going to be 102 and 102. So when two lines intersect, if we know one of the angles, all of the other angles are either the same or supplements. And we can figure that out depending on where they're positioned in the lines, whether they're they form a straight line or if they're vertical from that angle. So with that in mind, we can look at a little bit more complicated situation. Let's just do this. That way I know I get them parallel. There we have two lines that are parallel. And I cut them by a third line. Now, technically, they don't even have to be parallel lines. Any two lines that are cut by a third line, that third line that cuts them is called a transversal. That word itself is not important. I will never quiz you on it or test you on it, but you'll hear in my math lab, they'll talk about, find the angle of the transversal or whatever. That's all it is. So if I know that this angle here is 62 degrees, this angle has to be 180 minus 62. Gives me 118. What's this one have to be? 62. It's vertical to the 62, or it's supplementary to the 118. This one is 118 degrees. Perfect, 118 degrees. So again, there's four angles formed, but they come in pairs. Also, you'll note how I indicated these. I indicated this with a single arc. That means that those two are the same angle, and then these two are both of the double arc, so those two are the same angle. How about down here? They have to be the same. If you think about it, this line started out on top of that line and is just slid over. Oops, that's not what I wanted. So if I slide it back down here, this angle here came from this one. So this one must be 62 degrees. What's this one have to be? 118. How about this one? 62. And this one? 118. Now, there's a lot of different rules out there for parallel lines cut by a transversal. A lot of different names and vocabulary. They would call these two corresponding angles. They would call these two alternate interior angles. They would call these two alternate exterior angles. They would call these two interior corresponding angles. Corresponding means on the same side, alternate means on opposite sides. And they'd have all sorts of rules. Corresponding angles are equal. Interior corresponding angles are supplementary. Alternate interior angles are equal. Alternate exterior angles are equal. Corresponding exterior angles, which would be this one and this one, are supplementary. Well, I'm throwing that out there very fast because I have no intentions of you memorizing those rules. This is gonna be my claim to fame. Hoff's rule. When two parallel lines are crossed by a transversal, the 8 angles that are formed, each pair of angles is either equal or supplementary. And on a test or quiz, I will never give you a case where it's like questionable. Like here, it's pretty obvious. Well, this one here, this one has to be equal. It can't be supplementary. This one has to be supplementary. There's no way it can be equal. I'm just going to wing it and get these close enough to parallel. So I want you to find angles A, B, C, D, E, F, and G. So first thing, let's name all the ones that have to equal 107. B is 107. G is 107. And E. Very good. So those are all the ones that have to be equal to the 107. What's A have to be? 73. And we got that how? 180 minus 107 gave us 73. So then, of course, all the other ones are 73. Of the 8 angles formed, there are only 2 unique measurements. Now, another property we can come up with is in a triangle. And we'll talk about this more when we look at triangles more. But there are 3 angles formed. Those 3 angles must add up to 180 degrees. And we'll look at why that is more at a later date when we look at triangles more in detail. But if this is 71 degrees, and this here is 57 degrees, I probably technically should do this, so it's marked as 2 arcs, so they're different angles. What's this third angle up here have to be? Well, let's do 71 plus 57 is 128. So yes, 180 minus 128 is 52 degrees. So it's 52 degrees. Any questions? So find this angle for me. What do we get? 23? Again, 86 plus 71 is 157. So 180 minus 157 is 23 degrees. Now that we're warmed up, I gotta get that a little bit closer to parallel. Pretend those two lines are parallel. What? Now that you're all warmed up, yes. I want you to find. It goes A, B, C, D, E, F, and G, H, I, J, K, L, M, N, O, and P. It's really not as tough as it looks. It really isn't. I swim. Don't poke the bear. So let's just start up here. What's A have to be? 129, because those two have to be supplementary. They add up to 180. B is 51, and C is 129. Now this is a right angle, which means H, this is 90 degrees, right? H has to be 90 degrees, because they're supplementary. That makes a straight line, so those two have to add up to 180. So then G has to be 39 degrees, which makes D 141, because G and D form a straight line. They have to add up to 180. So E is 39, F is 141. Now down here it's just a matter of matching this one up with this one. We have 51, 129, 51, and 129. How about down here? 141, 39, 41, and 39. Not nearly as bad as it looks. That looks like a great time to take a break. It's 4:20 now. Let's start up again at 4:50 or 4:30. 4:50. That'd be a heck of a break.